Okay, in this presentation, I want to give you an overview of research methods. And one thing I'm trying to do in this course is introduce you to the methods, the basic ideas of how we go about testing our explanations for how the world works, and preparing you. There's a course on research methods later where you go in depth, but I want, as part of the survey of IR, to cover this and give you some of the principles, if you will, of how we do these things. And that should set you up for the eventual research methods course. Okay, political science is a social science, and IR is part of political science. And what does it mean to be scientific? Because we don't look like a science. And there's always this debate, can you study politics scientifically? And people, blah, 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 blah. Look, my view of it is, let's just start with, here's literally a textbook definition of what scientific research is by King, Cohen, and Verba. Uh, Scientific research is designed to make descriptive or explanatory inferences based on empirical information about the world. So we describe things. We say, hey, look, we look around the world and we see that democracies don't tend to fight one another. That's a description, right? We're not explaining why, but we're saying democracies tend not to fight one another. Then we get into an explanation. Well, why is that? And we use theory for that, and there's various explanations. I won't go into that. But, and we're making inferences, right? Because we're never fully examining these things, or, you're not like they do in a lab, although in a lab they make a lot of inferences too. But we're making these inferences about the world. We're looking at the world and saying, okay, what this means is, and there's a logical inferential leap to a conclusion from the data. You try to make it as small a leap as possible, but there's always an inference involved. And it's on empirical. Empirical means data, observations of the world, facts, if you will, things that we see in the world. Now, to make it simpler, one of my professors back in the day, kind of legendary, he was older at that point, taught us a course on political science, the scope of it. And he, I asked him in his office one day, I said, at Rochester, we have people that do these game theory things. We have people that do heavy methodology, heavy quantitative research. And then we've got Dick Fenno over there who goes and lives with senators, does massive field work. And I say, what is it, talking about Rochester, because he was big on selling us as our own little discipline. But I said, what is it that's the unifying thing? And Rochester said, Riker said, well, when we utter a sentence about reality, we do something to prove it's right. Now, I then immediately called him. I said, yeah, but in science, we don't ever prove anything. We test and try to falsify things. He said, "Da, da, 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 da." Just in general, that's what we're trying to do. I'm like, all right. And I like that he was a little imprecise. But that's the thing you try to do here. And that's what methodology is eventually, when it's all said and done, that's what we're trying to do. Okay, there's theory and methods. And the course goes into both of those, and that's intentional. And there's actually separate courses in each of these in our program. Theory explains relationships between phenomena. And that means it says why. It tells us why things are happening rather than just observing that they happen. And this usually involves causality. And that's very much what theory gets at. Theory is the primary thing that establishes causality. The relationships are often unobserved. And in fact, there's a definition of theory that says it explains observed phenomena in terms of relationships with other unobserved phenomena. And so we're trying to say, hey, there's something you're not seeing here, right? And in in the hard sciences, this might be like, well, we don't understand this unobserved thing. Well, if you go back to germ theory, germs before people came up with a theory that, hey, there are these little things out there that are making people sick. And so for a long, long time, it was germ theory. And then the theory encouraged them to, make microscopes and to do tests. And eventually they did observe germs infecting cells and observe germs in places. And so they did observe it. The point was it was at that point unobserved. And this is an important thing that theory does, is it tells you where to look. It tells you the facts that you don't know. It creates from an unknown unknown, it creates a known unknown, to use Rumsfeldian terms. So, and this happens most obviously and explicitly in terms of producing hypotheses. A theory will say, look, this is what we think is going on. And a hypothesis is an observable relationship predicted by the theory that can be tested empirically. That's what hypotheses are. And so that's the role of theory in kind of a positivist scientific method to produce these hypotheses. Then comes methods. Well, what's methods thing? Well, methods examines phenomena and looks for observable relationships. This is what it does. It observes, it looks for relationships. That's what statistics does, finds correlations or patterns in data. And but in terms of the scientific method, the important function of methods is to test the hypotheses predicted by the theory. They put theories to the test, finding more or less support for them. Right. So that's the broad overview, and the two go hand in hand. That's why I always say it's better to take the theory course before the methods course, because the two are intimately linked in our scientific approach to the world. Scientific method. Hey, speaking of scientific method, in high school or college, you had scientific method in the lab where you had hypothesis and you tested. That was a very limited part of the whole thing. But the broader scientific method is theory produces hypotheses. Empirical research tests those hypotheses. And it never proves it, right? But what you try to do is you try to falsify the theory, right? And it sounds weird, but that's what I mean by test. And for theories to be taken seriously, they have to be falsifiable. Your theory has to, in some way, be testable, or else it's like, all right, that's a theory, that's an idea, but it doesn't, we can't test it, therefore we don't know if it works. And so that is, and it doesn't come out in all the research, but that is supposed to be what we do. We try to falsify things. And when we fail to falsify a theory, we get more confidence in it. We also like to talk about rival theories. We like to have different theories and test them against each other. And so a really good methods paper will have maybe 2 different or 3 different theories and have hypotheses from each, and then test those hypotheses and find out, hey, which theory does the data support? Because the thing is, because you can never prove a theory, right? You also can't disprove a theory without a better theory to replace it. And that's very much part of hard science. Once upon a time, scientists look at light and they said, light's a wave, but a wave implies a medium. What's it a wave in? Because we know it goes through the vacuum of space. How does light do that if it's a wave? Because sound doesn't. And so they said, well, there must be something out there that we're not observing yet. Let's call it ether, that is a universally present medium for light. And so scientists started finding ether, and they continually failed to find ether. And then somebody came up with the stupidest theory ever. Hey, maybe light is a particle that acts like a wave, which is stupid, right? That sounds very, what we would call ad hoc. You just made it up to explain something you can't explain otherwise. But that would, and they went and said, well, all right, if it's a particle, we should be able to separate a particle out. And they came up with some laser mirror in argon gas experiment that isolated a particle, and you saw it fly out to the side. But that is how they tested photonic theory, which it turns out to be the one that we now think is right. Takes a theory to beat a theory. And when you look at the history of science, there are a lot of crazy ideas out there. There was ether, there was phlogiston, which was the ever-present substance in flammable items that was released in combustion. And no, but for a long time they thought that until they came up with the oxygen combustion theory. So anyway, enough of that. Rival theories are important. It takes a theory to beat a theory. And theories, as I say, we never prove them, they just get more or less support. Now, there are two styles of research that you will see. One is quantitative, and I beat you up in our course with quantitative stuff, right? And quantitative research depends on numerical measurements of specific, well-defined and limited variables. And the important thing is not so much the numbers part, but the variables part. That when you see a quantitative study, they have got very clear variables defined, and those variables have come from theory, right? The theory said these are the things that are important. And then they define those things and operationalize them. And I have a whole presentation on how that works. But you come up with something that you can say, all right, here is something that we can observe and code into a number. And it because you're getting limited numbers of variables and limited well-defined things from cases, you can actually look at lots of cases, right? You can reduce World War II to 5 or 6 numbers, right? And you can do that for all wars. And therefore, you can test over a larger data set. And the function here is very much we're going to test hypotheses to see if the hypothesis holds, if there's support for it across a broad number of cases, what we call large N. N is the number of cases in any data set. Large N, we like those. And that's kind of the goal of quantitative research, is to get these broader views and to test theories. Now, qualitative research, that's when people just write about stuff, right? And you probably like reading that stuff more, especially when you're starting out. And these are case studies, and you might call them histories, but we like to call them case studies. And they just talk about, hey, here's what's going on. They don't depend on numerical measurements. They collect a large amount of information on a particular case in context, right? That's the key advantage of a qualitative thing, is you're looking at this information more in context, although this is a much more subjective process. But you have a large amount of information in context. And this can be useful when maybe variables are not well specified, right? And maybe not as well defined. And there are also cases like when you have something new, you often have to start out with qualitative research into it. When we're saying, all right, what's going on here? We have this new thing of cyber warfare, right? And so we have to look at that case before we can say, in some context, in its raw state. And then over time, you might start identifying variables, theories. So one thing that you can do with qualitative research is start developing theories. Another thing you can do where theories exist is you can say, all right, we have these theories and we've got some support for this theory, but maybe there are a couple cases that don't fit. Let's look at those. Try to figure out what's going on. Or maybe there's a case that fits and you want to say, okay, here's the theory in the abstract. How does this play out on the ground? And so you can, the best case studies employ theory to try and explain the world and to get some nuances that maybe isn't in the general conclusion of the other. So both of these approaches are valid, and both can be done scientifically, even the qualitative stuff. And that's a very important thing. If you seek to do qualitative research, I don't know, on your capstone paper at the end of the program, coming at it in a way that is, still scientific. What do and what would that be, right? So here's what, good methods, right? This is not an exhaustive list, but for now, just these are some things. Good methods builds on theory. I really say it involves theory. It's never, even though when you get a methods textbook, it's all about data and analysis and a lot of statistics. You got to build on theory. And that's why I say you take the theory course before the methods course. And when you do a paper, you get theory. And if you read the quantitative stuff I've assigned, there's almost always a strong theory section at the beginning. Maybe they're not coming up with it, they're testing someone else's, but the theory is incorporated in that way. Then a key thing is we need a systematic examination of facts, of data, of cases, whatever. Systematic, logically laid out steps that you say, I'm going to do this, I'm going to do that, and I'm going to do the other thing, right? You don't just read up on the subject and say, this is what I think is going on. You read up on the subject and say, all right, let's examine this aspect and let's do A, B, and C, and we'll come up with an answer, right? So being systematic, and that's very important in a case study. You almost have to do it in quantitative research because it's laid out in kind of a cookie cutter approach, but this is very important and you want to be able to do this, okay? One advantage of it is when you're systematic, your results become more transparent. And this is an important standard for this type of research, that it be transparent, that I can see what you did. I understand where you got the information. I got to understand what that was, and I understand what you're doing with it. And when you tell me, hey, these are the things I've done, I'm not just taking your word for it. I'm not in any way dependent on you. I can look at it myself and see what you did. And that's what we like to see. And in the laboratory world, they talk about reproducibility. If someone does an experiment, someone else will try to reproduce it. Transparency is our reproducibility in social science, right? So we want to have a key reason to use this a systematic approach is that it is transparent, and you want to be clear while you're laying out those steps to make sure you are being transparent. You also want to potentially disconfirm something. Our methods is not rhetoric. We are not trying to prove a point. We are not advocating for a position. We are doing to the best of our ability. We are letting the world test our hypotheses, or letting the world convince us of things. And when I've had students write research papers, the best ones are the ones where the student comes in and I had a student who was convinced that President Clinton had not done enough to dismantle Saddam Hussein's weapons of mass production, and he wanted to go and look at those efforts. And I could, all right, well, look at this and look at, we created a systematic approach to look at that case. By the end of it, he's like, oh my God, they did everything they could. And I said, this is wonderful because you've gone at this the right way. You've looked at things that could potentially disconfirm your hypothesis or your initial inclination. That's why that's very important. We don't want to amass things that support our position. That's what lawyers do, and that's why lawyers make good politicians. Poor political scientists is also why political scientists are not very good politicians usually, because we're going to actually test things. So you always want to keep that in mind when you go through this. Could you be dissuaded? You start with a hunch. Everyone has an idea what's going to happen, right? In this stuff, you got theory. That's what theory's for. It gives you your prediction. And the thing is, are we going to let the data disconfirm it, or are we just going to collect everything that supports it and then we're doing nothing but advocating? That's why, and the last thing is, we're always agnostic about results. We're always agnostic about how much we know, because we know how limited these things are. We have a theory, it gets some support. Have you considered rival theories? If you've considered the existing rival theories and they've had less support, well, now you're more confident of your theory. But at the same time, it's a theory. And so we're always saying, all right, we can do more. We can look at more. We always talk about supporting a theory, not proving it. But this is what I mean about being agnostic. And this is a key thing to learn. And I think it's part of why people don't like experts, is because experts will hem and haw, because we don't know. The more you study, the more you learn how much you don't know, right? When you don't know, when you haven't studied much, you think that things are obvious. And the more you go in and research it, the more you learn, hey, all right, you do learn a lot of things that aren't true, that you thought, you do improve, but you also become a little bit more reserved in your certainty, right? And that's why so many of the things you read, a lot of students complain. These guys, they come up with these, they hedge, and they seem mealy-mouthed, right? And they're not making these bold declarative statements. This is the way it is. And I'm like, well, that's because we don't believe it. We know too much about it to be too confident. So, that's why I say you want to be agnostic. Okay, so those are some of the things. I hope that this kind of gives you an idea of what methods is, and as you go through the program, we'll concretize this a bit and hopefully get you uh, good at, I can't think of a better, get you good at doing it, right? Inculcate a proficiency in producing good methodological research. How about that for a professor sounding way of saying it? And I hope this has helped you.